Hello friends, welcome back to my channel, and in this video we will solve a problem involving LTI systems. It involves convolution and time scaling properties of the Fourier transform, and let us do it step by step. So the problem statement goes like this. It says that a causal and stable LTI system whose impulse response is h of t, it produces an output of y of t if the input is given to a x of t. So now if you give x of 0.5 t as an input to the another causal and stable LTS system whose impulse response is h of point t, we are asked to find the resulting output. So to summarize, let me put that in a block diagram. So what is given? We have an LTA system whose impulse response is h of t, and for that x of t is the input and y of t is the output. Okay, that we already know. Now question is, if you give, I have another system whose which is also LTI, and it is also causal unstable. So that fellow's impulse response is h of 0.5 t. Now question is, if you give x of 0.5 t as the input, what is the corresponding output in terms of y of t? So that is the question. So let us solve this by using the Fourier transform, and also in the Fourier transform we will take the help of properties of convolution and also the time scaling. So first let us see time scaling property. How does it go? Yes. So time scaling property says that if x of t and h of t has a corresponding Fourier transforms as x of f and h of f, time scaling property says that Fourier transform of x of at, which is scaled version of x of t, time scaled version of x of t, is equal to 1 by modulus of a times x of f by a. So frequency domain, it gets scaled by a factor of a. So if a is a scaling factor in time domain, 1 by a would be the scaling factor in frequency domain. And similarly for h of at, what is the Fourier transform? That would be 1 by mod a times h of f by a. Same rule applies here. So I have written that explicitly, but that's okay. So now what is the convolution property? What does it say? If you have an LTS system h of t with input x of t, the output of the LTS system is nothing but y of t is equal to x of t convolved with h of t. Okay, for this and the previous properties, what did I do? I will paste the link where I have given the complete detailed derivation and analysis of these two properties. I have solved many problems also, so I'll provide the link there. You can thoroughly enjoy these two properties there. Okay, yes, but let's come back to the problem. So what are the convolution properties say? If you have an LTA system with impulse response h of t and input x of t, output would be equal to y of t times y of t would be equal to x of t convolved with h of t. This is already known for us because we should have studied this in LTA systems. But question is, in frequency domain what happens? So in time domain, if you have a convolution like x of t convolved with h of t, in the frequency domain, that would be nothing but a basic multiplication, which is nothing but x of f times h of f. Let us repeat that. If you have a signal y of t, which is nothing but convolution of x of t times h of t, then in frequency domain the corresponding Fourier transform of y of t would be y of f, and that is nothing but the Fourier transform of x of t, which is x of f, multiplied with Fourier transform of h of t, which is h of f. Okay, so indirectly we can say that convolution in time domain is same as multiplication in frequency domain. Okay, right. So now let's go back to the problem. So what is the question here? Question is, if you have an LTA system with impulse response h of 0.5 t and the input x of 0.5 t, express the output in terms of y of t. So that is the question. Okay, so first let us write the frequency responses of both input and the impulse response. Okay, so input is what? It is x of 0.5 t. What is the corresponding Fourier transform according to the property? So because here a is 0.5, you can easily see that Fourier transform of x of 0.5t would be 2 times x of 2f, and in a similar way we can see that Fourier transform of the impulse response, which is h of 0.5t, would be 2 times h of 2f. Okay, so that's a direct result. Okay, now what is the output? So question is, what we are, this is a system whose impulse response is h of 0.5t and input is x of 0.5t. What is the output? So first let us see what happens in frequency domain. So let's assume that output of this system is z of t. So what is z of t? Z of t is nothing but convolution of the input, which is x of 0.5t, with the impulse response, which is h of 0.5t. So that is what we have written here. It is x of 0.5t convolved with h of 0.5t. So again, if you go into the frequency domain, what happens? We have to take the Fourier transform, and hence Fourier transform of the output, which is z of t, would be equal to Fourier transform of x of 0.5t multiplied with Fourier transform of h of 0.5t. Why? Because convolution in time domain corresponds to multiplication in frequency domain. Okay, but in previous slide just now we saw that Fourier transform of x of 0.5t is how much? 2 times x of 2f, and Fourier transform of h of 0.5t would be 2 times h of 2f. Okay, now let us substitute these two results here. So Fourier transform of x of 0.5t is 2 times x of 2f, and Fourier transform of h of 0.5t is 2 times h of 2f. So simplification will give us that z of f is equal to how much? It is very simple, right? 2 times 2 is 4. 4 times x of 2f times h of 2f. So that is the step 2. So what is step 3? So we got z of f to be 4 times x of 2f times h of 2f. Okay, so let us write the given z of f in this fashion, which is nothing but 2 times of 2x of 2f times h of 2f. Okay, why? I'll just tell you. Recall that what is the output of the original LTI system? Y of f, that would be equal to how much? X of f times h of f. So if you compare this with this, what is that you observe? You observe that this x of 2f times h of 2f is nothing but how much? Y of 2f. So just we'll replace that here. So what happens? So we will get this result to be equal to how much? 2 times 2 will be there as it is, but x of 2f times h of 2f is how much? X of 2f times h of 2f would be y of 2f. So that result we got. So what is that we got? We got z of f to be equal to 2 times of 2y of 2f. Okay, right. So now let us take the inverse Fourier transform. Before we take the inverse Fourier transform, again recall that Fourier transform of x of 0.5t is 2 times x of 2f. In a similar fashion, we have a signal like Fourier transform like this, like 2 times y of 2f. So what will happen if we take the inverse Fourier transform? So 2 times y of 2f should give you y of 0.5t, because we are using the time scaling property. So what will happen? You get, if you take the inverse Fourier transform, z of f will become, z of f will have z of t as a signal, and 2y of 2f will have y of 0.5t as a signal, and this scaling factor 2 will remain like this. So this would be the corresponding output of the second system. So let us summarize what we got. So we are given that we have an LTI system with impulse response h of t and y of t, h of t and input x of t, and the output we assume to be y of t. So now our question is, how do you, what is the output of the second system whose impulse response is h of 0.5t and the input is x of 0.5t? So by taking the help of time scaling property and the convolution property, we proved that the output of that system to be 2 times y of 0.5t. Okay, so in this video, what did we learn? We learned how to use time scaling and convolution properties of the Fourier transform to solve the problem involving LTI systems. So I hope you found this useful, and if you did, please like, share and subscribe for more content like this. Thank you.